Okay. Today, inshallah, we will continue discussing the stepper motor. Last class, we discussed the variable reluctance stepper motor, how it works, what is the construction of the machine, and we discussed the different operating modes. We discussed full step operation and the half step operation. Today, inshallah, we will discuss the another type of stepper motors, which is permanent magnet stepper motor. The objectives of this class is to understand the permanent magnet stepper motor operation for the two different topologies, which are unipolar permanent magnet stepper motor and bipolar permanent magnet stepper motor. So what is the meaning of unipolar and bipolar permanent magnet? This is what we are going to describe, and we will describe the operation of each type similarly as we made for the variable reluctance stepper motor. We described last class that variable reluctance stepper motor has only iron rotor. There is no permanent magnets or electromagnets in the circuit. So only the stator winding or stator core has some poles or electromagnets that can be energized using external supply, and by means of a power electronic circuit we can control the energized pole. Control means energize or de-energize. For permanent magnet stepper motor, the rotor construction is cylindrical type. It's not salient like what's in the case of variable reluctance one. So for the permanent magnet, the rotor itself is cylindrical, and the magnets are inserted in the rotor in order to make short pass between permanent magnets and the electromagnets of the stator, and this will help to increase the machine torque. So this is the advantage of permanent magnet compared to variable reluctance, as we described the drawback of variable reluctance last class. So this is the advantage of permanent magnet compared to variable reluctance. It has higher torque and power compared to variable reluctance one. Right. What are the different configuration? One of the most well-known permanent magnet stepper motor consists of 2 phases in stator and 6 poles on rotor. So the stator expected to be wound by 2 coils. Each coil will be wound on 2 opposite poles or 2 opposite teeth, and by the end we are going to connect this coil in 2 different ways. First way, as in figure 1, as you can see, coil 1 will have 2 terminals or 2 halves, coil 1A and coil 1B, and by means of power electronic circuit we can energize coil 1A only and keep coil 1B not connected to any supply. This means the current will flow from point 1 to point A, and it will be open circuit for the part of 1B. So only 1/2 coil is energized. So for now, if we wound 2 opposite poles by 1 coil, it's expected when we have current in this coil to have 2 different poles, N and S. However, for this case, because we have only 1/2 of coil energized, we will have 1 polarity. So there will not be any other half polarity or another pole in the opposite of the machine. And this means that the end of the first pole will be the reverse polarity. Or we can control the motor by means only of one direction torque, as we are going to describe on the graph of the machine. However, for the case number 2, or in figure 2, we have one current moving in all over the winding. So we can supply the coil from the direction 1B to 1A, or we can reverse the polarity of the current from 1A to 1B. This means if we have a tooth at this portion here, this tooth can be N or S, and the tooth for the other part of the coil, or the end of the coil, can be also N or S, because the current can be reversed. For that, we can say this type is bipolar, because at each tooth we can get two different polarities, N or S. However, for the unipolar, all of time we will have one direction for current, which means the one half will act as N pole all of time. It cannot be converted to S pole, and the same also for the other half. So we have N for 1A or N for 1B. So this is the difference between unipolar and bipolar. So each phase is wounded on two teeth, as we described before, and the winding can be connected to operate the motor as unipolar or bipolar, as described by this configuration. The power circuit of the converter connected to the phases will be described at the end of this class. So this is the first example for the unipolar permanent magnet stepper motor for the full mode operation step. Let's assume we have stator, like shown here. We have first half of the coil, which is A1, and the second half, which is A2. So when we energize one half of the coil, we expect to have a polarity for this tooth only, and the other three teeth will be de-energized. So this means now the pole M will attract the first or the nearest S pole in the rotor. As you can see, the rotor here now, because we have 6 teeth, or virtual teeth, because it's completely cylindrical, but the as you can see, the poles are inserted in the magnetic core like that. So for this type, when we supply one half of the coils, as you can see, it will attract the polarity S all of time, because N cannot attract N. It has to attract only S. So this is the first step in our motion, and we will consider this as reference. So for now, when we energize one half, which is A1, and keep other 3 halves without any supply, so the other 3 halves are 0, we expect to have the reference position as shown in this figure. If we start energize the next half or next pole, which is B1 here, so we need to energize B1, which means this pole will be in order to understand or recognize the machine rotation, we have to go to one step before in order to understand how the machine will move. So now we are going to disconnect this pole, de-energize this half. so there will not be any polarity here. And we will supply B1 in order to have N at this portion. So it's expected that this pole has N polarity will attract this S. It's the same configuration like what we have described before. The angle between A1 and B1 is 90 degrees, and the angle between this S pole and that S pole is 120 degrees. So the difference now between 90 and 120 is 30 degrees. So if B1 attracted the part S, the rotor will move 30 degrees, as can be shown in this section. Is there any problem in this operation, شباب? Is it clear? Any question regarding the movement? Okay. Right. Second, so we made now this step. When we energize the half B1, the machine moves 30 degrees. By the same way, we are going to energize the coils or the motor pools by the same sequence, which means we started with A1, then B1, so we will continue in the same direction. So A1, B1, A2, B2, and so on. And if we supply the pools or energize the machine in that direction, in counterclockwise, we expect that the motor will move in the clockwise direction, as has been happened for the first case. And let's assume energize the third case, which at step number 3, to energize A2, which means this part will be N. So in order to recognize the operation, we have to go to the previous step. So we have to get a log to this figure. As you can see here, we still have 30 degrees between this pole S and A2. So when we supply A2 and de-energize B1, it's expected that the rotor will move by 30 degrees again in order to keep S at the same or close to the pole N of half A2. So the machine will continue moving another 30 degrees and so on. So for this kind of operation, which is called full step operation, the motor is moving by 30 degrees, and the relation of the step angle can be applied to this configuration. You remember the step angle relation we described last class, which is 360 multiplied by ns minus nr divided ns nr. So this is the full step operation. As you can see, now the rotor is coupled only from one side. So we have 4 sides, but the rotor is coupled only from one side. If we would like to increase the torque, we can start coupling this rotor from 2 sides, for instance, or from 4 sides. So how we can do that? Let's see the other operation. So this is the full step operation of the unipolar. For the half step operation, we described last class. Half step, it means the motor is going to move with half of the step angle of the full step operation. So if the full step operation here has a step angle of 30 degrees, we expect to have 15 degrees motion for half step operation. How can half step operation obtained? The same like we have described in variable reluctance motor. As you can see, the sequence of pulses for the full step operation was 1 and 3 zeros. The third step is the same to the second step in the full step operation, 0, 1, 0, 0, which means the rotor will be in the same position of 30 degrees, and we can make logic OR between the first and third pulse patterns in order to obtain the half step. So we expect to supply half coil A1 and half coil B1 in order to make the operation of the machine at half of the distance of the full step. So this is the first step, the same like in the full step operation. And when we need to make it 15 degrees, we are going to energize both of half coils A1 and B1 together. Right. For now, as you can see, S is the same at the same angle of N for half coil A1. However, S in this portion is 30 degrees apart from B1. So when we supply both of halves together, we expect that the rotor will move by only 15 degrees in order to be in equidistance between the stator tooth or stator teeth. So as you can see here in this figure, the rotor has moved only 15 degrees, and the phase difference between the bool S and A1 is 15, and the same phase difference from the other side is 15 degrees. So the rotor is in equilibrium at this position. So we could make the step angle 15 degrees by making the same sequence of pulses as variable reluctance motor. So first step will be A1, then the step after is A1 with B1, and then B1 only. And by the same way, B1 A2, then A2, then A2 B2, and B2, and then B2 with A1, and return again to A1, which is the same like step number 1. So from 1 to 8, the rotor has moved by 115 degrees, and we can continue till the end of motion to the revolution. So from reference 0 up till 345 degrees, which means we have another step to reach to 1 complete cycle, and this is the full operation or full revolution for half step operation. So it's very important, Shabab, to recognize what the pulse sequence in order to move the machine for 1 complete revolution. Any question, Shabab, for the half step operation?
Doctor,
تفضل.
is there anyone talking? Oh, it's my voice repeating. We can consider that it only moves in one direction, right?
We described last class for variable reluctance, and it's the same also here in the permanent magnet. We can move the rotor in both of directions. Yeah. Let's go to the full step before of this slide. For this case, when we energize A1, then B1, the rotor moves in that direction. Is it right?
Yes.
Let's energize after A1, let's energize B2. So it's expected to have N bool here. So it will attract the first S. So the machine will move in the opposite direction. Okay? Right. So simply, if you would like to reverse the motor operation or motor direction, you can simply reverse the sequence of pulses. This is for any type of stepper motor. Okay? And also the same for half step operation. If you energize A1 and B2 together instead of A1 and B1, you will find this bool will be N, and it will attract that S bool. So the rotor will move 15 degrees in the opposite side. Okay?
Okay.
So the direction control شباب can be adjusted using the sequence of pulses control. يعني for now we use the sequence A1, then A1 B1, then B1, then B1 A2, then A2, and so on. So we are moving in this direction. If you need to reverse the motor, so move in the other direction. So start from A1, then A1 B2, then B2 alone, then B2 A2, and so on. Okay? So just reverse the sequence of pulses. For the unipolar up till now, for the full step or half step operation, you can see that the rotor is coupled either from one side or from two sides. However, we miss to couple the motor from the four stator teeth, which means we still can apply a technique to have more or much more torque and power. However, this cannot be obtained for unipolar case because unipolar case, as we described, the circuit will allow you only to move a current in 1/2 coil. Or by another way, we can say only 1/2 of the coil can be energized. So you cannot energize one coil at the same time, one complete coil at the same time. This is for unipolar motor. However, for bipolar, it's all of the coil will be connected together, and it's expected to have two poles or two polarities at the same time. So let's switch to the bipolar motor. So for bipolar motor, when we energize one complete coil, which is for coil 1 for instance, which is wounded on the pole A2, and by the normal winding way, the coil is going to be wound on the A2 in the reverse direction. So from A1, if A1 is N, the polarity at A2 has to be S. And if we reverse the current in coil number 1, we expect it to have A1 as S and A2 as N. So this means at the same portion of A1, the polarity can be N or S. So for that we call it bipolar stepper motor. However, for the unipolar, all of time when you energize the half coils, you will find only one polarity at each tooth. Right. Let's describe the operation now for the full step. Simply, the first step will be the same like in unipolar case. When we energize coil number 1, you will find coil number 1 means A1 is N and A2 is S. So instead of adding zeros and ones, we have to assign the polarity of poles. So here, when we energize coil number 1, so A1 will be N and A2 will be S. And the coil number 2 is not energized, so we expect no poles in coil number 2. So you will have N here and S in the other side. So the N here will attract the very closed S, and at the same time S will attract the closed N. So the rotor will be in equilibrium in this case, and we can consider this is the reference case for the motor here. In order to move the motor in full step operation, we need to make energizing for one coil each time. So let's de-energize coil number 1 and energize coil number 2. If you would like to move the motor in the clockwise direction, you have to supply the pulses or the sequence of pulse in counterclockwise, which means if this is N now, you have to make this tooth as N in order to move the machine in clockwise. So in order to make B1 as N, this means we are going to energize coil number 2, where B1 is N, so B1 is N here, and B2 is S, and coil number 1 is de-energized. So if this is N, it will attract the first close S, and if this is S, it will attract this N, so the motor will move 30 degrees in the clockwise, as can be seen here in this part of figure. So this is now one full step operation. As you can see, the rotor is coupled from two sides. Similarly, the rotor can continue operation to move another 30 degrees when we continue moving in the same direction. So we start from step number 1, N was here, and second step N moves to B1. We need to move N to tooth A2, which means the current will be reversed in the coil number 2. So, in coil number 1. So it means that for coil number 1 at step number 3, A1 will be S and A2 will be N. For that, you can find that the rotor moved another 30 degrees in the same direction, and so on by the same way. So it's expected to have here also 12 pulses for one complete cycle. The advantage here for the full step operation of bipolar compared to unipolar, that we have higher power, because all of the windings are for one winding, I mean, all of the winding is energized, and two sides are coupled or wound together. For the half step operation, by the same way, we can make one step between the first two steps in the full step. So step number 1 and 3 here are the same like step number 1 and 2 for the full step operation. In order to move the motor only 15 degrees, we need to energize the two coils together. So here for step number 1, this is N. For step number 2, N moves to B1. So in order to make half step, you need to make the two steps together by making OR gate, which means you have to make at step number 2 here to keep A1 N, B1 N, and A2 S, B2 as S, which is this figure now. So the motor will move by 15 degrees in order to make only 15 degrees between S and N from both of sides here. And the same also will be from the other sides. So in this case, we could make coupling for the rotor from 4 sides. And this is the maximum power or torque can be obtained in this case. Okay, شباب. So this is the half step operation for bipolar permanent magnet stepper motor. Any question, شباب? Okay. So the same notes like what we have already described for the variable reluctance. As you can see, to reverse the motion direction, the sequence of pulse has to be reversed or changed. So we can change from A1, B1, A2, B2 to A1, B2, A2, B1. This will reverse the direction of the motion. Also, for the full step operation, only 1/2 coil is energized at each step. However, for half step, we need to energize 1/2 and then 2/2 and so on. This is for unipolar. To operate the motor at half step, you need to follow the following sequence: A1, then A1, B1, then B1, and so on. We have higher torque in bipolar case because, as we have described, the rotor is coupled from 4 sides in case of half step, or from 2 sides in case of full step. So it's higher torque compared to the unipolar motor. However, the torque produced by half step is pulsating type, either in unipolar or bipolar. And this is one of the drawbacks of the half step operation for any kind of stepper motor. Now this is a power circuit. We need to make the operation for the unipolar permanent magnet stepper motor. As we have described, we have coil number A with 2 terminals, A prime or A and B. Okay, like what was in the example. And if you would like to have it exactly like in the tables, this terminal will be A, and that terminal will be B, and the same also here, it will be A and B. But this is coil number 1 and this is coil number 2. This is the way of what we have made in the tables. Right. So let's assume we have here 2 halves, and this coil we have also 2 halves. And as you can see here, this point A is connected to that point, and the current will flow only in one direction. So when this switch is turned on, A1, it will make a direction to flow current from V plus to the common point, moving with this half coil and going to this direction to ground point or 0 point. As you can see, because there is a reverse side here, the polarity cannot be reversed. So we have only one direction for current pass in this half coil. The same also for coil or half coil A prime. If the switch of half coil A prime, which is Q2, is turned on, so the current will move from the common point through this half of coil and moving through switch to ground. The same is also for coil number 2. So this is the well-known circuit for unipolar stepper motor, permanent magnet stepper motor. So the current here, these diodes with the VCC are connected only to protect or to avoid current moving in the reverse direction. Okay, شباب. For the bipolar permanent magnet stepper motor, we need the following circuit in order to reverse the current at each coil. So as you can see, for coil number A, we have Q1, Q2, Q5, and Q6. So we need 4 switches for each coil. It's like the same for 4-quadrant operation of DC motor. We need full H-bridge or 4-quadrant circuit in order to reverse the current in the coil. The same is also for coil number B. So we need, this circuit is called dual H bridge, dual H or dual full bridge. This is used for stepper motor, or this circuit, and you can find it in the market, and you can operate on also two DC motors with the same circuit, because the DC motor has only one armature circuit, which is corresponding to one coil of the stepper motor. So this circuit is well known, شباب, and it's very cheap. You can find it in the market. يعني you can find it, it's around 30 riyals for the up to, I believe, up to 10 amps, 12 volt for stepper motors or DC motors. Okay, and it's very cheap and can be coupled to any digital controller in order to control these motors. So the drawback of this circuit compared to the unipolar circuit, that we have higher number of switches, which means the cost is high compared to unipolar. However, this, because of the mass production, you may find the circuit with the same price, because the cost of power electronic elements for low rating power is very cheap now. And as we described, you can find this circuit by only 30 riyals, 40 riyals, like that. So this is the circuit used with the bipolar permanent magnet synchronous motor. Right. Comparing the two circuits together, as we can see, the bipolar has higher number of switches compared to the unipolar one. This affects the cost, but as we described, the cost became very cheap now. However, the higher number of switches in the same circuit will increase the losses of the power electronic circuit, which means we'll have lower efficiency for the electrical drive system for the stepper motor. So this is one of the drawbacks of the bipolar stepper motor circuits. So for now, we describe the different motors and the power circuit for each type. The relationship, as we have described, we have only a relation of the step angle, and number of steps can be calculated from the step angle. Okay, and also we described last class the relation of the machine speed. Okay, so these are the all the relations needed to recognize or to calculate anything for stepper motor. So this is our problem. It will be quiz number 5. It's simply three-phase stepper motor. Three-phase means we have 3 coils in stator, shown in figure. This is the figure. It's supplied from a chopper to provide the proper full step operation. So we are going to make 3 phases for this motor. So it's expected to have coil number 1 connected to one switch, okay, in order to supply this coil. The circuit that we have described in previous class, and the chopper is connected to a supply of 24 volt. So the circuit will be simply one DC supply of 24 volt and connected in series with switch and coil in order to supply this coil. And the drawn current per phase is 0.2 amps. So each phase or each coil will draw 0.2 ampere. If the chopper is controlled by switching frequency of 500 Hz, calculate the motor speed, the step angle, the number of steps per revolution, and the consumed power, considering the duty for 3 phases. Okay, شباب, this is the required in that quiz. I think it's very easy, and as we agreed together, all quizzes and exams will be considered as take-home exams. So we expected to have the solution, inshallah, by next week, next Wednesday at 4 p.m. Any questions, Shabab? So the summary of the today class, we have described the different types of permanent magnet stepper motor. We described the operation of different type permanent magnet stepper motor for the different step angle, full step and half step, and the power circuit of different types of permanent magnet stepper motor. And I will stop recording, and if anyone has any question, we can discuss it together.